In the last video, we started with a limit that was written at the top of the board, and we imagined that somebody had challenged us, that they didn't believe that was the limit, so they gave us an epsilon value, and they said, this is my tolerance for how close I want your y values to get to that limit. Bet you can't make them get that close. And we showed that we could. We found a delta value, which was essentially the tolerance for the x values, and we said if our x values were within that distance of delta from the number they were approaching, then our y values would be within that epsilon value of the limit. We did that for a specific epsilon. We're now ready to do our first formal proof where we're going to keep epsilon as a variable, so we won't have a numeric value for it. Okay. So here's the limit that we're going to prove. We're looking at the limit as x goes to 2 of 1 minus 3x, and it equals -5, which we can confirm very easily. If we were to plug in 2 for x, we would get that. This is a continuous function. Want to just point out, this is a linear function. That's all you will be responsible for in doing formal proofs. A linear function, or possibly a linear function with a hole in it. We've seen that sometimes we could have a rational function that simplifies to a linear function with a restriction on the domain. Okay, that you'll be responsible for doing formal proofs for. Unless you're in the honors section, you won't be responsible for formal proofs for anything else. Those of you in the honors section will explore some more complicated functions in some of the worksheets. Okay, so here's basically the scenario. We're going to suppose, once again, that we have claimed this, and somebody is coming along and challenging us. They're saying, oh yeah, I don't think you're right. I bet you can't get that close. Okay, so they're going to give us an epsilon bigger than 0. But rather than specifying what number that is, I'm just going to keep it as an arbitrary number. Now I still have to do what we did last time, which is I have to find a delta that's going to work. So my goal at this point is to find a delta, which will also be a positive number, such that if 0 is less than the absolute value of x minus 2, x is approaching 2, so I want here the distance between x and 2. So if that distance is between 0 and delta, then the absolute value of f of x, actually, didn't give it a name, I gave it a formula, of 1 minus 3x minus a -5. So that's my function minus the limit. So that would be the vertical distance between the y value on that line and the y value that we're claiming is the limit. And I want that to be less than epsilon. Okay, now this is an if-then statement. If this thing happens, then this thing will follow. This part comes first. So when we do a formal proof, we're going to have to introduce this number delta that we found. Now, it's not going to be a specific number. We're going to have to just describe it in terms of this other number, which isn't specified. All we know about epsilon is that it's positive. We're going to have to somehow describe delta in terms of epsilon and then demonstrate that it works, going this way. If-then statements have a direction. You start with the if part, and you show that the conclusion, the then part, must be true. But if you think about the work we did last time, is we started with the epsilon, and we started with the epsilon inequality in order to figure out what our delta was, because we knew more about that, because we had a specific number for epsilon. Now here, I don't have a specific number for epsilon, but my goal is going to be to try to describe delta in terms of that. So I want to think of it as it's like I know what epsilon is, and I'm trying to work with that. So my informal work, I'm going to start with this, and I'm going to work backwards. So if I ask you to write a formal proof, I'm going to be looking for two things. I'm going to look for the informal work, which is how you figure out what delta is going to work. And for that, you're generally going to start here and work backwards. But then I'm going to ask for the formal proof where you go in the right direction. Now let me just make an analogy. I'm saying I want to get from here to here. Okay? So imagine it's like on a map. I want to get from point A to point B. But when I read the map, it's kind of confusing because I'm sort of overwhelmed by all of the roads that lead from A. There are so many of them that, I start following them and they don't seem to lead me to B, and it's difficult. But I look over here at B, at where I want to go, and I see there is one road that leads into town B. Well, what I might do then is I might just follow that road backwards and say, that's how I'm going to connect my ending point and my starting point. But I did it backwards because it was easier to start here. Okay. So that's essentially why we're going to be starting with our conclusion in our informal work. But starting with your conclusion is a big no-no in formal proofs, because if you start with your conclusion, there's nothing to prove. You're where you want to be. Okay. So I'm going to have to then demonstrate that it works the other way. And to continue with the map analogy, the reason I need to do that is just because I can show that I can get from B to A doesn't mean I can necessarily reverse that. In traffic situations, there's such a thing as a one-way street. If this is a one-way street that goes from B to A, I'm not allowed to just reverse it and use that as my path to get from A to B. And in math, there are lots of things that we can do that we can undo, that we can go in either direction. Okay? But there are lots of other things that we can do that we can't undo, that we can't just reverse. Okay? So after we find a delta that we think might work in our informal work, we're going to do a formal proof to basically check and make sure that the route that we took was not a one-way street, that the delta that we found actually does work. Okay, so I'm going to just label. This is going to be my informal work. And I do want to clearly label it and distinguish that from my formal proof. Okay, so I'm going to start with this. So we have the absolute value of 1 minus 3x minus negative 5 less than epsilon. I'm just going to simplify that. I'm going to explore what it means for this to be true. Now, of course, minus and negative is just plus. So that becomes the absolute value of 6 minus 3x less than epsilon. Okay. And I think I'm going to just swap the order of those things, simply because if I look at where I'm going, I'm trying to get to an inequality that involves an x minus 2. That has the x first and then the number. So I'm just going to rewrite this as negative 3x plus 6 in the absolute value being less than epsilon. Okay. So now we'll come up here. I'm going to just factor out a negative 3. Still inside the absolute values. So that becomes negative 3 times the quantity x minus 2 inside the absolute values is less than epsilon. I'm kind of liking this because I'm seeing an x minus 2, and I know that's sort of what I'm hoping to get to. Okay. Now, this is the absolute value of a product. Absolute values distribute over multiplication. Don't distribute over addition, but they do distribute over multiplication. So this is the absolute value of negative 3 times the absolute value of x minus 2, and that's got to be less than epsilon. Very important that that is still in the absolute values. I did not factor a negative all the way outside of the absolute value. The left-hand side here was something that's not negative. It's still something that's not negative, because that's two things that aren't negative multiplied together. Okay. The absolute value of negative 3, I happen to know, is 3. So I could write this as 3 times the absolute value of x minus 2. That's the thing that I'm going to want to be less than epsilon. So what I'm going to do is I'm going to divide both sides by 3. Very pleased that that's a positive number I'm dividing by so that the inequality doesn't change. And I get the absolute value of x minus 2 needs to be less than epsilon over 3. Now, it looks like that's what I want my delta to be. Remember, the first part of the inequality just tells us that x isn't 2, and that's because I don't care what happens at 2. In this particular problem, it wouldn't be a problem if x was 2, but if I had a line with a hole in it instead of just a line, then I might need to specify that. Okay, this part of the inequality right here, this is the part that's telling me that x is close to 2. And I'm thinking this is telling me how close it needs to be. So I'm thinking that's my delta. That's my standard of closeness, or my tolerance for my x values. Okay, so that's the informal work. Okay, I'm going to end this video now, but we're not done with the problem. All we've done is we found a delta that we think works. What we need to do now is show that we can go in the correct direction. Because here, we started with our conclusion and we worked backwards. We need to make sure that we didn't take any one-way streets along the way. Okay, so in the next video, we will do the formal proof part of this problem, introduce that value for delta, and prove that it works.